Next, we'll discuss a method of a different type, which is called the fixed point method. Okay, so in this method, we are trying to transform our original equation, which was f of x is equal to 0, into an equivalent equation g of x is equal to x for some function g. Okay, so for example, if for this equation I set g of x is equal to f of x plus x, then obviously if I solve the equation g of x is equal to x, it is the same as f of x is equal to 0. This typically is not the best way, of course, to obtain this function g, but this simple example shows that we can always transform an equation in this form into an equation in this form. Okay? So now we can focus on the equation g of x is equal to x instead of f of x is equal to 0. And the iteration that we will consider for this equation is the following. So we start with some point x0, okay? Then we generate a sequence of points x1, x2, and so on, xk plus 1, where xk plus 1 is expressed through the previous x, which is xk, as follows. So xk plus 1 is equal to g of xk. So this is what we called a fixed point iteration. So why is it called a fixed point iteration? Because a point like this, where g of x is equal to x, is called a fixed point. So now when we consider this iteration, and assuming that g of x is continuous, then we can easily show that if this sequence xk converges, so let's say xk converges to x star, sk tends to infinity, then we can show that if we have this, then x star is a fixed point for g, meaning that x star is given by g of x star. Okay, so how do we show this? If I consider x star, then x star is given by the limit of, let's use k plus 1 here, when k tends to infinity. So when k tends to infinity, we can write xk plus 1 or xk, it doesn't matter. But for convenience, let's write xk plus 1, because this way we can express xk plus 1 as g of xk when k tends to infinity. And then by continuity of g, this is the same as g of limit of xk when k tends to infinity. And then the limit of xk is x star, right? So this is g of x star. Okay, so this shows that x star is equal to g of x star, so x star is a fixed point. Okay, so whenever the method converges, it does converge to a fixed point, and now a fixed point is what we need to find, right? So because we converted our original root finding problem into a fixed point problem now. Okay, so the question is, when does the method actually converge? So let's consider some illustrations first to see that the method may not always converge. So also this will show how the method proceeds, in fact. So let this be x, this will be our g of x. Because our iteration is xk plus 1 is given by g of xk, when we compute each next xk, it is convenient to use this line here, which is the line given by y is equal to x, in order to show each next iteration on the x-axis. Okay, so let's say if I start with x0, right, so then my x1 will be what? Just g of x0, right? So g of x0 is given by this here, so this is g of x0, and my x1 is actually g of x0. I need to project now this g of x0 into x-axis. And because this line gives me the points where y is equal to x, so this will be the point where we have the value of g of x0 for x. And this is our x1, right? Our x2 will be g of x1. So what is our g of x1? G of x1 is this here, and to show it on the x-axis, we again use the line y is equal to x, so this is our x2. Okay, the point we are looking for here is this point, right? So because this is the point where x is equal to g of x, so where these two functions intersect, so this is our g of x and this is x, right? So where x is equal to g of x is this intersection point. So this is our root that we are looking for. And we can see that we started on the right from the root, right? So then we went to the left from the root, but we moved closer to the root. So now we are going back to the right of the root. So we got x2, which is even closer to the root than x1. So now the next iteration, we need to find g of x2 and project it into x-axis. So this will be our x3. And we see that we are moving closer and closer to the fixed point. All right. This is what we call the oscillating convergence. So the method converges here, but it does so in the oscillating fashion. We go to the opposite side of the root every time. But in some cases, we may have a divergence also. So let's look at an example where we have a divergence. So if I consider an example that is kind of similar, but let me make this function quite a bit steeper. So this is again y equals x. So this is our g of x. This is x. Okay, so if I start with some point x0, so this is g of x0, gives me x1. So this is x1, right? So then this is g of x1. So this gives me x2, g of x2, which gives me x3, and so on. So we see that in this case, we are actually moving away from the fixed point. So this is our fixed point. So let's denote it by x star here. So we started with x0 that was pretty close to x star, and then we moved to x1, which is farther away from x star, x2 is even farther away, x3, and so on. You see, we diverge. So in this case, we have the oscillating divergence. We can see that depending on what function you get, the method may either converge or diverge. And this is different from the bracketing methods. In bracketing methods, as soon as we identify the interval where there is a root, we are guaranteed that the method will converge to that root with any given precision, right? So now in this case, we see that divergence may be a problem. Therefore, we need to characterize when does the method diverge, or when does the method converge. We saw that if it does converge, that it converges to a fixed point that we are looking for. And the question is, when does this happen? Next, we'll provide a good characterization for when we have the convergence. And to provide such a characterization, we need another classical theorem from real analysis, which is the mean value theorem, or MVT. So this theorem deals with continuously differentiable functions. Say we have a continuously differentiable function on the interval AB. What the mean value theorem tells us is that if I draw the line between A f of A and B f of B, then we can always find a point on the interval AB where the tangent line for f will actually be parallel to this line here. Okay, so we can see that, say, somewhere around this point, we will have tangent line for f, which is parallel to this line that we drew here. Okay, so if f is continuously differentiable, then there exists some point c on the interval AB such that f prime of c, so which is the slope of the tangent line, is the same as the slope for this line, which is given by f of b minus f of a divided by b minus a. All right. So this is the mean value theorem. how do we use the mean value theorem to establish conditions for the convergence of the fixed point method? So let's consider this next. In the fixed point method, we have xk plus 1 is given by g of xk. Okay, so if I consider the error of my fixed point method after k plus 1 steps, so xk plus 1 minus x star, where x star is the fixed point. So we have x star is the fixed point, the point to which we want to converge, right? And of course, this is the error, right? So this is the absolute value of the error after k plus 1 steps. Then this is the same as, instead of xk plus 1, I will write g of xk. And then x star is the same as g of x star. So we have the equality here, right? So, and at this point, we can apply the mean value theorem that we just mentioned. So now this is the same as g prime of ck multiplied by xk minus x star. Okay, so because by the mean value theorem, there exists some point ck between xk and x star, right, such that g prime of ck is equal to g of xk minus g of x star divided by xk minus x star. Okay, so just apply the mean value theorem here. So now, if we assume that, so this is an important assumption, so assume that the derivative of g at x, the absolute value of the derivative, is less than or equal to some constant c for any x. All right, so if we assume that, then we can have the upper bound on the error, xk plus 1 minus x star, will be less than or equal to, so because this is less than or equal to c now, this will be less than or equal to c multiplied by xk minus x star. Okay, so now we express the error after k plus 1 steps through the error after k steps. And we can keep doing this. Okay, so for xk minus x star, I could do the same exercise here and express it as g of xk minus 1 minus g of x star. Then it would be equal to g prime of some c k minus 1, right, multiplied by xk minus 1 minus x star. And then again, because the derivative is less than or equal to c, it would be less than or equal to c times xk minus 1 minus x star, so which is c square xk minus 1 minus x star. So, and this was because xk minus x star is equal to g of xk minus 1 minus g of x star, right? So which is by mean value theorem for some ck minus 1 between xk minus 1 and x star, it is g prime of ck minus 1 multiplied by xk minus 1 minus x star. All right, so this is less than or equal to c times xk minus 1 minus x star. Okay, so this is what we used here. All right, so but I can keep going like this. We can go down to x0. So you see, first we started with xk plus 1, then we have xk here, then we have xk minus 1, and so on. C to the power k plus 1 multiplied by x0 minus x star. All right, so the error after k steps is less than or equal to c to the power k plus 1 multiplied by x0 minus x star. And you know, c was just the upper bound on the derivative value for g. Obviously, if c is less than 1, then we'll have the error xk plus 1 minus x star will converge to 0 as k tends to infinity, right? So therefore, we can see that if the derivative is bounded from above by some constant which is less than 1, then we have the convergence. All right, so then for sure we'll have the convergence to a fixed point. In fact, it is very important to have the derivative of g which is less than 1 for the convergence, because if it is greater than 1, then we can see that there will be divergence. Okay, so let me give you an example in Excel which illustrates this point. So we'll consider a fixed point iteration. Say let's look at the point 3. So x is equal to 3, right? So, and then I will write down some fixed point iteration for this point. Let me multiply it by 0.1. So I multiply 0.1 by this 3 here, and then I subtract 0.2. Okay, so this will give me 0.1. So if I multiply by 30, then obviously we'll get 3 still, right? So we started with a fixed point here. At every iteration we get 3. Then let me just pull down this formula. So I expect to get 3 every time here, right? So, but now let's see what happens if I pull this down more. So we get 3 as expected every time. So, but at some point we actually start getting some error. All right. In fact, at 15th iteration we already see that there is some error, and then this error propagates in our computations. So now if I pull it down a little more, we see that this fixed point iteration in fact diverges to plus infinity. Okay, so and this is a very, very simple iteration. So now let's analyze this by looking at what exactly we do in this iteration. So we had xk plus 1 was equal to 0.1 xk minus 0.2 times 30, which is the same as 3 times xk minus 6. All right, so and of course x star equal to 3 is the fixed point for this iteration. So and we just have a linear function, right? So let me illustrate this graphically. So we have point 3 here. This is y equal to x. At point 3 our value is 3. At 0 it is minus 6, somewhere here. So our g of x is given by 3x minus 6, right? So this is our line here. All right, so and we actually started at point 3, and then, you know, if the computations were precise, we would always stay at point 3, right? So, but because here the way we represent things on the computer, so usually the numbers are represented on the computer in the binary form, and for example, if you take a decimal like 0.2, it doesn't have an exact finite representation in the binary format. So 0.2 is approximated with some number that is very, very close to 0.2, but it's not a precise value of 0.2 in the binary form. And because of that, we have a slight error, and at some point we start deviating from 3. So we essentially get some point which is very close to 3, but not quite there. As a result, we will move to this point here, then to this point here. And you can see that we start diverging very quickly. All right. And the reason for this is because the derivative of g of x is 3 here, and it is greater than 1. All right. So here we have a round-off error coupled with the divergent method. It leads us to some serious problems. Even a very, very simple fixed point iteration where we have the integer fixed point, right? So, and only deal with simple decimals here in this iteration, we start having problems, all right? So we need to make sure that whenever we transform a root finding equation f of x is equal to 0 into equivalent equation g of x is equal to x, we need to make sure that we select this function g in a way that the derivative of g is less than 1, so then we guarantee the convergence. Okay,